Welcome to CS1033 Program Fundamentals module, and we will now discuss the divide and conquer in programming lecture, which is part of the problem solving series of lectures. Let me first give you the contents. So we will start with an introduction to the concept of the divide and conquer for problem solving. And we'll look at some classic algorithms, starting with quicksort, then merge sort, and an algorithm for fast multiplication of large numbers. The last one, fast multiplication large numbers, as I'll explain, you'll find that it's very important in several specialized applications. Now, to give you a quick introduction to this phrase, divide and conquer. So the origin of the term is attributed to the Roman Emperor Julius Caesar, who basically dealt with a very large problem of having to govern an empire. So the Roman Empire, basically. So the problem, because many of the states that were part of the empire were rebelling against the emperor, as usual the case, and the way he tackled the problem was to divide it into smaller problems, smaller states, and deal with a smaller problem at a given time. And the overall solution of a stable, undivided empire was built using these sub-states. So basically that's the story, okay? Just like any story from history, you should make up your own mind, right? Moving on, in computer science, what we do is actually divide, conquer, and combine, okay? So we would take a problem and recursively divide it into sub-problems, 2 or more, okay? So these sub-problems are quite similar to the original problem. So that's the basic approach or the paradigm. The process of dividing the problem into sub-problems, we will continue until the problem becomes tractable or problem becomes something simple enough, we can solve it easily. So it's up to us to decide what is the level at which the problem is easy for us to solve. And at that point, we will stop the breaking up of the problem into smaller problems. The recursive subdivisioning is how we conquer the problem. Okay, so the concept you should understand. So we are not solving our problem by getting into a simplified level. Actual way of problems solving the problem is this dividing the problem, how we divide. Okay, so once we have divided the problem into these sub problems that we can handle, and once we have solved them, we will combine these partial solutions until we get the full solution. So remember, while it is very important to divide the bigger problem into smaller problems so that we can handle them at some level of simplicity, it is also important to remember that the solutions should be such that they can be merged to give you the final solution. So this divide, conquer, and combine paradigm should be used in that manner to solve problems where actually the partial solutions can be combined to give the final solution. This use of divide and conquer approach is widely used for applications such as sorting, searching. So sorting, you know what it is, not to put things in a particular order, searching in a large collection to find a specific item, and also parsing. That means, so if you have a text input, so a lot of strings, you may want to break these strings into what we call tokens. So that's what we have here. For example, if you look at this text we have here, okay, so we can pass this text into words by separating them with separators. So the space here is a separator, the full stop is a separator. So like that we can, and a new line is a separator. If we take the full set of text like that, so that is passing. Okay, so there are, and these kind of applications or these kind of tasks, sorting, searching, parsing, are at the core of many of the solutions we develop. Whenever we are trying to solve a problem in the everyday applications we have to deal with, like managing a transportation system, managing a financial system, managing a industrial system, supply chain management, providing online education through Moodle and Zoom-like systems. So any of these large systems, they have a lot of sorting, searching, and parsing requirements in the highly complex solution that provide these services to us. So let's look at, as our first example, the quicksort algorithm. So this is a classic divide and conquer algorithm. Okay, so the input is an array of values, and the output would be the same array with its content sorted. So the input is in some random order, the output is in a sorted order, right? So let's look at the details of the algorithm. First, once we are given this array, so visualize this. So this is an array. So in each slot, in each storage location, you have value. Okay. So think of it as an array of 10 storage locations. Each location 1 to 10 would have some value in that, and they are not in order. Okay. And once we are given this array, we will select one of these locations as a pivot element. Okay, pivot element. How do we select this? Okay, so there is no specific rule on how to select the pivot element. You can use among many different options. For example, you can select from the array the leftmost element, like the first element, or the rightmost element, the last element, or the element in the middle, or some random element. Okay, so basically, as you can see, we are very flexible on selecting the pivot element. Then what we will do is we will reorder the elements in the array. So now we are selecting a pivot element. So we are basically selecting a location, and that location has some value, some item in that storage location. So all the values which are less than that value are put to the left, or before that element, and all the values greater than that are placed to the right or after that. Okay, so that's the task we carry out. So so this is called partitioning. Okay, so essentially this process will partition the big array into two small sub-arrays, right? So when we are doing this, actually, we might find there are other values which are equal to the pivot element. So when you look at the left-hand side, there is an element that you find is equal to the element. So we can just place it just after the pivot element we have selected or before. That's not a major concern, because the idea here is for them to be in order. So I will take you through an example, then it will be very clear to you what we are doing here. So the end of this partitioning operation, okay, so breaking it up into sub arrays with the pivot element at the middle. So this operation will always put the pivot element at the correct position with respect to the other values. So all the other values, if you take a pivot element in an array, all the values that are to the left of it are values less than that, and all the values to the right of that are greater than that. Okay, so mind you, the values to the left are not necessarily in order. They are not ordered. They are just less than the pivot value. The values to the right are not in sorted order, but they are all greater than the pivot value. So essentially, only the pivot value gets the correct position, guaranteed. Okay, other may just random name the correct position, but it is the pivot element that we are focusing on. So these two steps that we have discussed, selecting the pivot element and partitioning the array, we are going to apply recursively into sub-arrays that get smaller and smaller. So the same concept or the same algorithm gets applied. Here I have the Python code for the quicksort. So let's see what we are doing here. Okay, for example, now to partition an array, so this is my function to partition an array. I will get an array, and I will also get the array positions. The reason is this. Now I will get a lengthy array, with the original size of the array, but I will so initially I will get the full array. Okay, so let me show that. So initially I will get the full array. Okay, so starting so this would be the low mark, this would be the high mark. Okay, so now based on some criteria, I will break this array. Let's say I will select pivot point here. Okay, and then I have two sub arrays. Okay, so so this is one sub array, and this is the other sub array. Okay, now for the original array, this is the low pointer, this is the high pointer, and for the left hand sub array, this is the low pointer, and this pivot element is the high point. And for the right hand sub array, pivot point element is the low mark, and the original high mark is the high mark for this sub array. Okay, so this way I can always give different sub arrays for the processing. Okay, by defining what the pivot element is. So that's the idea behind passing the low and the high points. Okay, so the low and high are the two values that will get changed. Array will always be the same actually. Okay, so I can always pass the full array, but by defining the low and high, I say which part of the array is the part I want you to work on. Right. So now, as I said, I can pick at the pivot point the leftmost one, rightmost one, the median one, or some other random point. So here I have decided I will pick as the pivot point the last element in the array. Okay, so that's the decision I have made. You can decide to take the first one, the middle one. Okay, so in that case, the pivot would be the value at the high mark. Okay, value at the high mark. So this will give you the content of the array. Okay, you are dereferencing the array to get its content. Then I will be setting the index of the small element. So this basically to put the elements on the correct side. Okay, so I have defined the variable I, and no, low -1 is the index of the smaller element, and then I perform a repetitive operation where if the current element is smaller than or equal to the pivot, the values get swapped. Okay, values get swapped. So this is what happens in the partitioning. So basically, to put the values on the correct side. Next, I can now do the quick sort operation. Okay, so there is a condition to be checked initially. So because if as we are increasingly making the sub array on which we operate, at some point low and high would be the same. That means it is a single element array, single element sub array. So at that point we can stop our work. So so that is like arriving at the base case. So here otherwise, if so low is less than high means, well, you have an array on which you have to work on. Okay, so essentially the partition operation happens, and it will, yeah, so it is interesting to actually check what is returned. So you are returned here the smallest element index, and so that is the PIDX that is returned here. Okay, now so basically the pivot point pivot point ID, right? So so then the quick sort will happen to the left side. So low to pivot point -1 is the left side to the pivot point, and pivot PIDX plus 1 high is the right hand side of the pivot point. So you basically get a array to sort with a low mark and a high mark. You figure out the pivot point at which you should do the partitioning, and then you will say, okay, now go and quick sort the left hand side sub array and the right hand side sub array. Okay, so this is the idea. So now I have an example here for a small set of values, so I can show it on the screen. Let me show you the screen of running this. Okay. So this is the input I am giving: 10, 7, 8, 9, 1, 5. So they are not in sorted order. So now, as you can see, that is the input. This is the input to the array. Sorry, to the algorithm, and then you can see 5 has been selected as the pivot point, and all the values that are less than 5 are on the left hand side, and all the values that are greater than 5 are on the right hand side. They are not sorted, but they are all greater than 5. Okay. And so that's the trick that one would use. And if, for example, now next, when you use, say, for example, 7 as the pivot point, okay, you can see all the values to the left are less than 7, all the values to the right are greater than 7, and you can see they are not sorted because see, 8 is coming at the last element. And when you use 8, you can see all the values to the left are less than 8, all the values to the right are greater than 8. And when you have 9, similarly, all the values to the left are less than 9 and greater than 9 for the right hand side. And the sorting happens while you do this, because always the sub arrays, the small arrays, are getting sorted in the correct order. Okay, so so this is how the problem is solved. So yeah, you might see here recursion happening, the same function calling itself with a base case, but apart from the recursive approach, the key idea here is you have a large array to sort, break it up and sort a small array. Okay, so the idea here is not just to break it up, but to break it up in such a way you can merge the results. Okay, so partitioning it correctly is essential for the merging of results. Okay, so that's why ultimately you get the correct sorted array. Moving forward, we'll look at another algorithm. It is called merge sort. So this is another sorting algorithm based on the divide and conquer paradigm, and was invented by John von Neumann. I'm not sure whether you have heard the name already. Probably you have. So you should actually check what this scientist is famous for. He's famous for many things, in mathematics, in logic, in computer science, in computer architecture, and yeah, many different fields. He have made very important contributions, and he's famous for microprocessor or processor architecture. Okay, that's what he's most famous for. And if you look at the details of the merge sort algorithm, it has several actions. First one is, okay, obviously you get a list of items which are not sorted. Okay, so this unsorted list of items, so let's say n items, so that's an array of n items which are not sorted. They will be divided so that ultimately you have n sublist. Okay, so if you have n items and if you have n sublist, it is obvious that each sublist contains only one element. Okay, so that's one action you have to do. And a list of one element, of course, is considered sorted because that's only one element. No? And this is the terminating condition. Okay, for the division of the list. And then these sublists are merged in such a way that what is produced is a sorted sublist. So you have two sublists being merged, and that merging operation will give you another sublist which is now sorted, and so on and so forth, that ultimately you will end up getting the original list sorted. So we look at an example to see this algorithm in operation where the final output is sorted. So I have the code here. Let me first explain the code. So this is the definition of the merge sort function, where the input is the full array. Okay. So as soon as we get the array, we will check if the array length is 1. Okay. If the array length is 1, then that is a sorted array. Okay. But if the array length is greater than 1, it is still not sorted. Okay. Maybe values are in sorted order, but no, we can consider it. We haven't done the job yet. So that's why we check if it is greater than 1. And if that is the case, we will find the middle point of the array. So we get the length and divide. So this is the integer division. Okay, slash in Python is the integer division. So if it is 3, you get 1. If it is 4, you get 2. And if it is 5, you get 2, like that. Okay, integer division. Then with the midpoint decided, you will create two arrays, a left side array from the start to the midpoint. So you are familiar with this array partitioning notation of Python already. Okay, and then this is the right hand side, which is defined by giving the array partitioning operation mid and the colon to indicate that this is the range of indexes. Okay, so this is the start and this side is end. That would be the natural end of the array, the maximum value, and this would be the natural start of the array, the original start to the middle point. Okay, so now you have two subarrays, and you will call merge sort on the left side of the array and then on the right side of the array. Okay, so this is the recursive call that happens. And after, so our assumption is that when you come back from this sorting of the left and the right, within those sublists they are sorted. Okay, so the left hand subarray is sorted and the right hand subarray is sorted. Now we have to merge them together so that the contents are in order. So this is that merge operation. So we copy data from the temporary left and right to complete the merge operation. So so we have this while loop happening. So while there is elements in the left hand and there are elements in the right hand, okay, subarrays. Okay, so if any, suppose one is smaller, because it is quite possible that the array that got divided is not a even length one. So if it is an odd length one, then there will be one which is smaller. So as soon as one array is finished, this loop will exit. Okay, so basically we get the ith element from the left hand side and check whether it is smaller than the jth element on the right hand side. We just check that all ijk have been initialized to 0 here. Okay, so if the left hand side is smaller than right hand side, you just put that particular element, left hand side ith element, to the original array, ARR, at the kth position, and I is incremented. Okay, otherwise that means, so this the element on the left is actually bigger than the element on the right hand side, then what you copy is the right hand side one and you increment the jth index. And because now you have copied a value to the array at the kth position, then you increment the index k. Okay, so I, j, k are 3 index variables that you manipulate. So so at this point you have copied an element from either the left hand side or the right hand side to the original array. Okay, and you continue with this operation. Okay, so at some point you might exit the while loop because one side got exhausted, either the left side or the right hand side, depending on which one is shorter. Okay, so if it is, so once you exit, you check whether index I, which is handling the left hand side, is still less than the length of the array, which means there are some unaccounted for data remaining there, which means basically the right hand side array was the shorter one. If that is the case, you just copy whatever is in the left hand side to the remaining positions in the array. Or if it is the other way around, the right hand side you still have some elements remaining, then you just copy the elements on the right hand side, okay, to the original array, whatever the remaining values. So the idea is, by this time all the values that are smaller or equal to the either left or right, okay, so let me, okay, so let's see that we have broken into two, and the left is shorter than right. So by the time the left hand side is processed up to the same length, okay, so this length on the left hand side is the same as this length on the right hand side. The original array would have got filled up to here, okay, up to here. Now the remaining part to be filled will come from the left hand side remaining data, and this remaining data would be, the values of this data would be higher than either the left hand side whatever you have taken from this, or the right hand side values here, okay. So you can just copy them to this side. That's the idea. So so that's basically merge sort for you, okay. And so the slides have this simple test code. Let me show you an example here based on that. So this is not in solid order, as you can see, 15, 11, 7, 5, 9, 13, 15, 11, 7, 5, 9, 13. So this is that array. So this, so the red color values are showing how so it is showing how the processing happens, the order. So the original array gets partitioned to a left and right. And if you take the left hand side, it gets partitioned again to two parts. So the left is 15 and the right is 11 and 7. Then that gets partitioned. So as given in the algorithm, they get partitioned until a sublist is just one element. Okay. So as soon as the sublists become one element, the merging can happen. So as you can see here, now this 11 and 7, they get swapped and correctly get ordered, okay, in the merging process. And then it gets merged with the original 15, and then that also gets correctly ordered. 7, 11 and 15 is put to the right hand side. And if you look at this one, again 5, 9, 13 and 9 and 13 get divided. So now you have all single elements. So the it is at the single element point, yeah, it is at the single element point that the splitting or the merge sort calls end for the splitting. Okay, so these are the points at which they, so 1, 2, 3, 4, 5, 6, so 6 single element arrays from the original 6 element array. And then here the, yeah, you can see a bit of a useless type of work happening. So this is already in correct order, but yeah, this algorithm would anyway follow through to the next step, and thereafter we'll re-merge them to be on the correct order, of course the same order, and then the values will get merge here again. So as you can see, this part of the tree is kind of wasted effort, but no, that's how the algorithm operates. And then you have this sublist 7, 11, 15 and 5, 9, 13. So the merging will happen. So for example, 7 will be compared against 5, and because 5 is smaller, 5 will be put there, and the index will move to 9, this one, and this index will remain there, and then 7 and 9 will be compared. 7 is smaller, so 7 will be put to the original one, and the index will on this side will move to 11, and this one will remain at 9, and then 11 will be compared against 9, and then because it is smaller, 9 will be put there, and the index here will move to 13, and this index will remain at 11, and then 11 and 13 will get compared, and 11 is smaller, so it will come here, and the index will move to 15, and here the index will remain at 13. So 15 and 13 will be compared. 13 is smaller, so it gets put here, and then the last element, so this is the 15, which will come and it will get placed here. So that's how the merging happens. Okay, so so this is the merge sort operation. So now, before I go to the next example, let me show you the code being executed. I will share my browser window. Okay, so this is the same code I showed you. Okay, same code I showed you, except that I have changed the input array. As you can see, it's a bit longer now. So I'm not putting any partial results here. You can actually put the partial results by printing whenever you come out of a merge sort like operation. Let me just run this and show you. Okay, so now you can see that the original array, which is unsorted, is now the result is sorted. If I want to see partial results, I can actually put them put some code here to print left and print right. Okay, and let me run it again. So you can see that the breaking up of the lists into single elements have happened, and then merging is happening. Okay, and so the some partial merging is happening before the full merging happens, because as was shown, when you are going in the left hand and right hand side of the tree, certain partial merging will also happen. Okay, and yeah, so at this point, all the splitting of the array list into single elements have happened, and now only the merging is happening. Okay, so yeah, so you should try and experiment with the code which is available in the slide set to test how the algorithm works. So let me get back into the slide set. Yeah, so this is the last example. This is about multiplying large numbers. Okay, so exactly what do we mean by large numbers? So so there are a lot of applications that require multiplication of very large numbers. Okay, so when I say very large numbers, they are like numbers which are, say, 2048 bits long. So massive numbers. So if you consider the normal numbers we work with, so if it is, so I'm talking about actually integers. Okay, integers, not real numbers which are represented in floating point. So I'm just talking about integer numbers. So the normal integer numbers that are available to us are like 64-bit or long int, which is twice that, 128-bit. That is because now many of the microprocessors are 64-bit microprocessors, and operating systems directly support such values, 64-bit integers and 128-bit long integers. It used to be like 32-bit integers and 64-bit long integers, but there is a need for many applications to deal with much larger integer numbers, which are 1024. So actually they start from 512-bit, 1024-bit, 2048-bit, and going up to 4096 bits like that. So whenever you connect to the internet using the secure connection, HTTPS, that protocol uses cryptography, secure means of connecting the internet that uses this kind of large numbers. Okay, so I mean, you always connect to the internet using HTTPS for Moodle access, for LMS access, for Gmail access, for Zoom access. I mean, no, most of the websites are HTTPS. So you can see how often actually you use this kind of integers, and a lot of the computations you do are integer multiplications. So given that situation, multiplying these large numbers fast is a very important requirement. Now, if you consider conventional multiplication, which is called also long multiplication, it is very inefficient for very large numbers. Okay, it's not something that you can build a mathematical operations library and use it widely in your programs. Okay, so we need something better. Now, an algorithm for this multiplication of large numbers, large integers, and to do it very fast was developed by a Russian mathematician called Anatoly Karsuba in 1960. And the algorithm is called the Karsuba multiplication. It's pretty simple actually when you look at it, but of course, no, all great inventions seem to be simple ones. Somebody explained that to you, right? Okay, so the key idea behind the Karsuba multiplication is that when you multiply two numbers, you can do that using just 3 multiplications rather than 4 multiplications, which is the classical requirement. Okay, so I will explain what the 3 multiplication, 4 multiplication scenario is. But this reduction is a very important reduction, okay, because rather than doing, so if you are doing million multiplications, rather than doing 4 multiplications, doing 3 multiplications, a huge saving. Okay, now this reduction is achieved through basically a divide and conquer approach. Okay, so right, let's look at how we would multiply 2-digit base M numbers. Okay, so essentially, if you have a number, let me type this to very clear to you. Okay. So let's say number n1. N1 can be written as, so that's first number n1, x1 times, okay, put dot, that's times m. M is the base plus x2. Okay, so this basically the x2 is the x1 is the whole part, and the x2 is the remainder. Okay, so if you divide n1 by m, x2 would be the remainder, x1 is the whole part. Okay, So so that's one way to represent n1, and the number, into the second number can be written as y1 times m, the base, plus the remainder y2. Okay, so essentially now if you are going to multiply these two numbers, n1 times n2, you can see it will be x1 times y1 times m squared. Okay, so I'm going to write m squared like this. Okay, plus you will have x1 times y2 times m plus x2 times y1 times m, okay, plus the last one, x2 times y2. Okay, so you can see when we are multiplying two numbers n1 and n2, we need 4 multiplications. Okay, x1 to y1, x1 to y2, x2 to y1, x2 to y2. Okay, of course there is this multiplication by the base, but multiplication by the base is pretty straightforward. All you have to do is shift. Okay, because if the base is 2, generally the base is 2, and you just when you're doing binary operation, you just shift by the number of powers of m. So if it is just m, you shift by 1. If it is m square to the power of 2, you shift twice. Okay, like that. Okay, so to the power 1, to the power 2, to the power 3 would simply equal to shifting only. So that is a very, shift is a very fast operation, but multiplication is a very slow operation. Okay, because it's like repeated addition. So now there are 4 multiplications required. Okay, right, now let's see what happens with the Katsuba algorithm. So Katsuba's algorithm would get the value x1 and y1 computed. Okay, and let's call that f. Okay, so x1 and y1 that you have here is computed and it's f, and it will also compute x2 and y2, and that would be x2 and y2, that would be this one. Okay, and it is called g. Then it will compute x1 plus x2 times y1 plus y2, and the result will be h. So mind you, this is addition, so addition is not an expensive operation. This is addition, not an expensive operation. And then you have multiplication. So now you have multiplications. If you look at the multiplications, multiplication 1, multiplication 2, and multiplication 3. Whereas here you have 1, 2, 3, 4. We have only done 3 multiplications here. Okay, so now if you look at the operations that are happening here, let me type this here. So we have the f, and so f is x1 y1, so let me put it here, f, and then we have the g here. So let me put an arrow to show you where it goes. So so this is f is x1 y1, so it is this value, and g is x2 y2, it is this value. Okay, so we need this value to be handled. Okay, so essentially this is x1 times y2, x1 times y2 plus x2 times y1. Okay, right, times n. Okay, as I said, multiplication by base is a straightforward operation. So so this part is what you have here, right? Now if you look at this this multiplication, the h, okay, so if you look at h, which is computed as x1 plus x2 multiplied with y1 plus y2. Okay, so this is equal to x1 times y1 plus x1 times y2 plus x2 times y1 plus x2 times y2. Okay, so essentially now you have x1 y1 here, okay, which would be f, and x2 y2 here, which would be g. So if you take h minus f minus g, h minus f minus g, you essentially have this part, which is the part required here. Okay, and let's call it k. So the full computation where we need the values h, we need the values f, g, and k, we are able to obtain that using only 3 multiplications rather than the classic computation which requires 4 multiplications. Okay, so as noted here, raising the multiplication by base n raised to any power is just straightforward shifting. So that's the algorithm. Okay, pretty simple. Okay, now we do only 3 multiplications. Okay, just 3 rather than the 4 multiplications otherwise we have to do. Now that is the divide and conquer approach. Okay, so moving forward, to do these computations of f, g, and h, we can use recursion. Here I have an example of the algorithm running. Okay, the Karatsuba the function has been defined as Karatsuba, and the 2 values have been passed. Okay, and I have a rule here. Okay, what is my rule? If the 2 numbers are basically less than 99, okay, that's what I'm saying. Get the value x, convert it to a string, and if the length is less than 3, that means say 99 or less, I will do the multiplication directly. Okay, so just that rule I have created. Maybe that's the only computational power I have. So any number less than 99, I can directly multiply. Otherwise, I call up the algorithm. Okay, so the algorithm I explained, the Karatsuba algorithm, is implemented here. So the HF are calculated, and then K is calculated here, and the computations are happening. So I have an example here. So if I call the algorithm with 23 and 45, both are numbers less than 99. So directly the answer is given. Okay, directly the answer is given. But if I call it with two large numbers, so 123,456 and 987,654, two large numbers, then the Karatsuba algorithm runs. Okay, and the final answer pretty large is given in like in very few steps. Okay, and as you can see, I'll be either returning small values which I can compute directly because they are all less than 99, or I'll be computing values through recursion. Okay, recursion and any other compute. So there are two return statements here one and here one. So in here, basically, I am my operations are fast operations, because this raising to the power of 10 like operations are just shift operations. Okay, they are just shift operations. So they are not considered as expensive operations, and the other operations are simple addition operations. Okay, so in here it is just subtraction operations, and the other multiplications are based on the base. Okay, so 10 to the power something multiplied. So they are all shift operations. So direct multiplication of numbers, only small numbers. So this is the whole idea, that I will so that I'm only capable of doing small number multiplications, as well as the overall computation happens very fast, because now I don't use 4 multiplications as the conventional scheme, but just 3. So this is the Python code which you can use for testing purposes. Finally, I have an exercise for you to try out to see whether you understood this concept of divide and conquer. So essentially, so if you are given a set of points in the XY plane, okay, so you have the XY plane, and in that so this is the XY plane, and you are given, sorry, so you are given points. So right, so if you have these points, now the task given to you is to find the pair that is closest to each other. So you can use the Euclidean distance to determine the closest pair. How the shorter the distance, Euclidean distance, the closer they are. And one naive way of deciding that is you take the distance from every point to every other point. Okay, every other point. And this one similarly. Okay, so every point, so if there are n points, each point has n-1 distances to every other n-1 points. So you will have n points, so n into n-1 distances. Out of these you pick the shortest one, and that would give you the closest pair. But as you can see, that's a very nasty way of doing it. Very computationally expensive algorithm. So the requirement is for you to look at how to do this task through a divide and conquer approach. Okay, so that is the exercise for you to do for this particular divide and conquer approach to problem solving. So that completes the lecture.